Okay, hi, welcome everybody to the logic workshop, second meeting this semester. And today we have our own Hans Schoutens, who is going to speak about the model theory of categories. Right.
Yeah, thank you. Sorry that this is reminiscent of the last 2 years that I've doing this remotely, but I kind of got stuck here a little bit because we are in southern Florida, but east side, so the storm didn't hit us, but nonetheless flights were canceled and delayed and we didn't want to risk anything. So that's why we're here. I'm talking from here. Okay, so please interrupt me whenever you want. I do this all the time, so you have the right to do this to me too. And don't raise hands, just talk. I'll hopefully hear it then. So I want to talk about a new kind of thing that I've been thinking about for a year now almost, is the model theory of categories, because categories, of course, are considered as very foundational in mathematics. Set theory perhaps is the most foundational, but it is kind of bare bone foundational. Model theory, we logicians, of course, think of it as foundational with structures, mathematical entities that we study, but most mathematicians are not so familiar with that. So they rather think categories, that they can accept categories, I think, more than they can accept model theory. And if it's a foundational perspective on mathematics, then both are, then we should be able to translate from one to the other. But they're different. They're different in some sense. For instance, one big difference between model theory and categories is in categories, you don't have negation. Another difference is in model theory, you're looking at the structure and its elements and its subsets of the structure. In category theory, you don't even have elements often. These mathematical entities, they are just entities. They don't need to be even sets and more, but what you look really at is morphisms. So model theory says, I know a structure because I know its definable subset. Category theory says, I know a structure because I know it interacts with other structures that are similar. And how do these two, I mean, they're two different perspectives in some sense, so how do they combine? That's a little bit what I want to talk, what will also come up here in this talk. And somehow my goal is to actually incorporate category theory in model theory, which makes model theory the top guy, I guess. But the other way, it's also been done, by the way. Model theorists have used categories, and in fact, elementary topos, and so this whole internal logic, this is a whole field that has developed, where categories play a role, somehow replacing traditional model theory. So it can go either way. So it's my claim that it's that model theory is the top guy is perhaps not fully. I mean, you can mention, you can cite later. Okay, but let's move on. So category, perhaps for those that are not really exactly know what a category is. So category, I'll word it, denote them always like blackboard letters. It consists of two things. There are objects and there are morphisms. And instead of morphisms, I'm going to say arrows. Because objects, okay, you think about sets, structures, and mathematical identities. Morphisms, you think of functions. But very often they are not. They are just arrows, like arrows in a graph or something like that. They are not maps. They are just, well, arrows. Okay, and so the data of objects and morphisms, that gives a category with some more things, but it will come clear what these other how these two interact with each other. Now I want to look at one particular type of category. That's and so I need one definition. So the definition is, what is a terminal object in a category? So that's an object. So I'm going to denote it as a star. You see why I choose this thing. So star is an object. So that for any object X in C, there is a unique arrow into a star, a unique arrow. Okay, so example. There's some echo. Do you guys have an echo too?
No.
Is it okay? It's not disturbing or anything like that? I turned off
Yeah,
this.
sounds good.
I guess
Probably
it's just
because you have two devices that you get feedback.
okay. So an example, of course, if you take the category of sets, the singleton, so the one element set is a terminal object, right? Because there's only one map from every set to that singleton, mapping everything to that one single element. When I say there is the terminal object, it's only up to isomorphism. Okay, so I'm kind of a bit vague here with unique is up to isomorphism unique, and so I don't want to go into these nitty-gritty details. So that's an example. For instance, another example that I will look at is the category of groups. There it is the zero group, the group with just one single element for the same reason. Okay, so there are quite a lot of categories that have terminal objects. So why is that interesting? Well, because there's a unique morphism. So among all the arrows, there are these special arrows that have this I call the codomain of an arrow. Codomain, and this is the domain of an arrow, right? And so these are among the arrows, there are what is this? Okay, I don't see this. Sorry, just bothering me. There are these morphisms that have a unique codomain, special codomain, and that completely determines all the objects, right? So this class of morphisms corresponds to all the objects. So the reason that I'm doing this so that I want to have a language in which I have only one sort, and the sort will be arrows. Okay, so how I'm going to now view a category C? So a category as an LCAT structure. So what is this language? Well, I have two predicates, domain, unary functions, domain and codomain. So these are unary. I have a composition, it's a binary. And I have, what else do I need? Oh, okay, yeah, right, I need my terminal object, and this is a constant. Now you say, okay, wait, it's supposed to be, every element's supposed to be arrows. So how is this terminal object an arrow? Well, there is, of course, this arrow, which is the identity. That's the unique arrow from the terminal object to itself. So actually, that's the one. I'm kind of identifying them already. So after a while, I'm going to immediately identify an arrow of this type with this as the terminal object as my codomain with its domain, which I call then an object. Okay. And so this is now the category. And so what are the axioms? So I'll do axioms in red. So one of the axioms says that, well, okay, so if you have an arrow, if you have, so F is now an element of my category. No, let me use a different notation. Okay, sorry. So let's what do I mean with an L structure? So an LCAT structure, let's call it early C. It's going to be a category eventually, but what is it? How does it LCAT structure? What is the axiom that I want to put on this LCAT structure? So remember, the elements of this thing will be the arrows in a category. Okay. All right. So what are the axioms? Well, the first axiom is that the domain of F is equal to F even only if the codomain of F is that special element, the terminal object, right? So remember, so we have here this arrow here, this special arrow, and the domain of this arrow is this arrow. The codomain of this arrow is this arrow. So everything has to be arrows, right? So the domain of an arrow is, in general, if I have an arrow x to y, oh, what is that for a weird thing? X to y, then the domain, so the domain of this thing is going to be this arrow, that's the domain, and this arrow is going to be the codomain, okay? And so if this happens to be an arrow of this form, then domain of F is just F. And that can only happen if the codomain is, I know I don't know whether this is confusing or not, but it just is saying what I was saying, is that you can identify an object with a special arrow into the terminal object. Okay, that's the whole thing. And such thing that satisfies this, I will call an object. Okay, so I have now my objects. Among these arrows are special arrows that are called objects. Okay, and then the other axioms are almost obvious. Well, first of all, well, the domain of any f and the codomain of any f are of course objects. And what else? Oh, if I have two arrows, say f and g, and the codomain of f is the domain of g, then I can compose them. So in that case, we can define the composition. You can think of this, therefore, this binary operation as partial, or rather, you say, I don't care what it is. If we're not in this situation, when the codomain is equal to from the first domain of the second, then I just ignore whatever the outcome is. And so in that case, of course, we have always think about this way, I guess, right? G compose F. So what is the domain of this guy? Right. So remember, this is supposed to be X to Y, and this is supposed to be Y to Z, right? This is F. So this is F and this is G. So this is supposed to be the domain of F, and the codomain of the composition is, of course, the codomain of the second arrow. Okay, and then we also say that this is an associative relation, and for every object X, there is a unique morphism arrow 1x from X to X, that X, the identity, let me just say it. It acts as the identity. And these are really just rewriting a little bit the conditions of a category. and so in other words, if you have a category, its arrows, if you have a category with a terminal object, its arrows will satisfy these axioms. And conversely, everything that satisfies these axioms is just a category. So if you have, so we had this structure C here, right? So this structure C, I can now associate the category C. The objects are the objects, stupid, right? And the arrows are the arrows. Okay, I hope you see that what I'm trying to say here, right? So okay, so let's look at an example here. Well, okay, I can look at examples, but I want to make it a revolutionary, a very, like, how do you say that, subversive definition. So definition. So from now on, again, I'm going to confuse a category with a model of this theory. So this is the theory of categories, which I call T-cat. Okay, so a category is just a model of T-cat, and I go from one to the other. Okay, so the definition, I say that a category C is universal if for any category D, so a model of my theory, if C is elementary equivalent to D, then D is a subcategory of C. So this is subcategory, I mean here. Now, I know that there are different ways what this means. It could mean it's isomorphic to a subcategory. It could mean it's equivalent to a subcategory, or this is an actual subcategory. Again, I'm not going to make distinction to any of these statements. So you'll see, it's kind of obvious what it is what we mean here. Now, okay, if your model theorist, you say this is nonsense because it's a first order structure. There are structures, huge structures by Lowenheim's column. You could use structures. How can it ever? And here I'm saying every elementary structure embeds in this one guy. How is that possible? Well, but notice that so as examples, of course, with the category of sets, right? And the category of groups, none of these are actually sets. They are classes. So that's the thing, right? So note that these are classes in the set theoretic sense. Okay, they are not sets. And so my models here, I'm allowing models to be classes. Don't ask me about the foundations of model theory of classes. I have no idea. I'm just assuming that that works. Okay, we can look at classes as models of a theory, and it's not. I'm not the first to do this and not say much about it, but okay. So now perhaps it gets a little bit more obvious that it is possible, that it could be possible. And now you might say, okay, I know sets, the category of set. So examples. Oops. Example. The category of set is universal, right? Because any category that's elementary equivalent to set is the category of sets. Well, Remember, in categories, objects do not have to be sets. Well, you say, okay, everything is a set. We are set. Set theory is foundational, so everything is a set. Okay, fine. You can still think of these as sets, but arrows do not have to be maps from this set. Whatever way you look at this set, it's not going to be a function. And so how do you know that if a category is elementary equivalent to set, if you have a model in my theory, in an L structure, so this is my language here, and I have a structure C that satisfies this theory and is elementary equivalent to this thing, how do I know that the objects are sets, and more importantly, that the maps, the arrows are actually maps? So now all of a sudden it's not clear that sets is universal, but it is. Okay, so I'm going to give you a second example where I can actually show it. This be the category of abelian groups. Okay, so I'm going to show you that it's a universal category. So claim it's universal. Okay. So what am I going to do? So how do you do this, by the way? What I want is some actions, additional axioms that somehow single out the category of abelian groups, and any other model that satisfies these axioms must necessarily consist of groups. That's what universal means. Okay. So I'll give so therefore let's work. I'm first thinking, what should I do? In the category of abelian groups, if I take a group, I get a new group by taking the product. Okay, direct sum. Okay, let me write the direct sum, perhaps. That's a bit. So I'm going to use the additive notation for abelian groups. Okay. So the direct sum is also a group. And moreover, I have a map that sends A, B to A plus B, the addition. Okay. But what is now important is that these guys here, so what is this? In an arbitrary category, what is the direct sum? Well, in our category, you have the notion of product. It's a categorical definition. I don't want to repeat it. You know it, or you can guess it, or but it is categorical. It just says certain arrows have to be, we have arrows going this and this way, commutative diagrams, and so on, and that's how you define a product. So this is just a product. So this is an object. This is the product of that object. What is this? This is an arrow in my category, because this is a group, this is a group, and this is a group homomorphism, but that's what needed abelian. I need abelian commutativity for that. And this is a group homomorphism, so it's an arrow in my category. I can talk about it. So in my category, so there is a, let's call it nabla, from the product of my, so for every object G, I have a delta G, which is a morphism, is an arrow in my category, which satisfies now, it is a group law. It gives a group law. So what does that mean? Well, it has to be associative. Okay, how do you do that? Well, if you, in categories, it follows just from the definition of product, you can take the product of three different things, and the way you do that is not important. Okay, so I'm kind of a bit not pointing that out here, but so we have this commutative diagram here. So what is this? Well, here I'm composing the first two elements and leave the third element alone. That's this map, the top map. The bottom map is just another composition. And here I do just the opposite. Here I take the, sorry, this should not be, sorry, I should denote this this way, right? This way. Yeah, I'm very bad with this notation. So I think this is what I want to do. And then here again, delta G. So let's just follow it on an element. I'm reasoning now inside groups. Of course, inside any category, I don't have elements, so I cannot reason in elements. But inside groups, so in blue, I can reason an A, B, C. That's mapped here. The first two are mapped to their sum, and the second is preserved. Then the downwards map adds these two. This is, so I should perhaps put it this way, right? I hope you see what I'm going here. This is preserved the first and added second two. And this is therefore mapping it to A plus B plus C. And I'm just saying that they are equal. That's the commutativity of this diagram. Okay, so what my claim is I can express by means of diagram that there is an associative operation. There's also an identity that is the zero. And there's also, there's another thing, of course, I have also another map, the map from G to G that sends A to minus A. That's also a group homomorphism because of a bit of commutativity. So it's also an arrow in my category. It exists. So I'm now claiming as an axiom that there exists an IG from G to G that is the inverse. And you now have to write the correct diagrams to express this. If you have ever studied Hopf algebras or anything like that, or formal groups or anything like that, you have seen all these diagrams and it becomes clear. So you're going to have therefore several axioms. This is an axiom, this is an axiom that expresses associativity. You can express commutativity, identity, inverse element. And so in other words, if you put all these axioms together, and if you have now something that is elementary equivalent to this category, it must satisfy these axioms because these axioms are true in this category. And this just shows you that you have on every object a group structure. So any category that's elementary equivalent to the category of abelian groups consists or is the objects have a group structure. So it's isomorphic to a category of groups, subcategory of groups. And that shows universality. Okay. Now this is a proof that it's a nice proof, and I think it's it gives the concept of group. So what this shows you is that you can distill from morphisms in the category of groups that are group actions, that there's a group on any object. Okay. Now, all this was actually rather trivial because I have the following theory. A category C is universal even only if it is preserved. It is preserved under alter products, arbitrary alter products. That's a big theorem, but it's not hard to prove. Let me prove it for you. Well, before I prove it, I do a claim. Let's look at alter products a little bit more. So let U be an alter filter.
Hans, can I ask a question?
Sure, sure.
What do you mean by preserved under alter products?
I mean that if you take an object, if you take objects in your category, you take their alter product, it's again inside the category. Does it make sense?
How do you make a sense of alter product in the category?
Okay, so you do it yeah, okay. You have to think of it as a structure, and then in the structure you can do that.
Okay.
Yeah. Okay. Okay. So so U is an alter filter on some index set. Doesn't matter what the index set is. And so let's look at this thing here. So this is the alter power. So I'm now again thinking of this C as a structure, and I take its alter power. So what it's a category again, because it's a category. And what are the objects in this category? The objects are exactly the alter products of objects of C with respect to this alter filter U. And morphisms are, or arrows, let's call them arrows, is the same thing, but now of arrows. You have to just, I mean, I remember this is some revelation that me and Joel had a decade ago or something, and then He might even have made a Met overflow topic out of it, but it's a kind of trivial observation that ultra powers of universes or categories consist of ultra products of the objects. Okay, so in some sense you could actually reverse it and say this is. I mean, there was. Alf, right? You were asking me this. I think this is perhaps the definition. The definition of an ultra product is an object into the ultra power. And in case we have sets or structures, then this corresponds to the original or the real ultra product. Okay. So I'm a bit vague here a little bit, but okay. So this claim I'm just going to leave and say it's actually just thinking about definitions. What it means that to be an element in an ultra power, and you'll see this is what it is. Okay, so now the proof. So if you're universal, proof. So suppose you're universal, then I have to show that you're preserved on ultra products. Well, let's do this. So of course, C is elementary equivalent with an ultra power. That's Washer's theorem. Okay, and therefore, by universality, it embeds in C. And this means, and by this claim, what are the objects in here? The objects are exactly ultra products of objects in C. And I'm just saying those guys are back in C. So that's what I mean with preserved under ultra.
But Hans, how do you know that in this embedding from CU into C, you're actually getting that the embedded image of CU is really giving the ultra product to the target category?
It doesn't matter. I don't need to. It only matters is that these guys. So this is a when I write a map of categories, I mean objects go to objects, right? It's a functor. Sorry.
So when you say closed under ultra products, you just mean that somewhere in the category there's an object isomorphic to the ultra product.
Yes. Okay. Yes. I said I'm going to sometimes be vague in what I mean with this ultra products. When I say two objects are the same, I mean to say they are isomorphic as objects. Yes. Yeah.
So it's not necessarily true that, for example, in this embedding that the ultra power is actually a product of the object you're starting with.
No, it could. That's true, I guess. Yeah, I just know. I just know this universality just means it tells me what it says is that the objects in this category can be made. This category can be made isomorphic to a subcategory of this. That's what this.
Okay.
What I mean with this.
Okay,
inclusion.
fair enough.
Okay. All right. So that's the simple, the direct application, I guess. But I agree there's a little bit of subtleties on the isomorphism and so on that be done. But the interesting one, of course, is the reverse here. So now what I have, okay, I have a category that's elementary equivalent to this, and I have to show that it is a subcategory of C, right? That's the property of universality. Okay. So what do? I use Kieser-Schalat. People, when I learned Kieser-Schalat, they say, oh, this is a theoretical result, nobody ever uses it. That's the only result I ever used in my life, except for Washer's theorem. So I like Kieser-Schalat. So the Kieser-Schalat theorem says this, that these two guys, because they're elementary equivalent, they have isomorphic ultra powers, perhaps from different ultra filters. But there are some ultra power that are isomorphic. In particular, it means that elementarily embeds in some ultra power of C. There's an elementary embedding in some ultra power. That's one consequence of Schalat. Now, this by the claim, this guy consists of is ultra products, and by my assumption, they are again objects of my original category C. So this guy, okay, I'm again using this arrow, which is really not. It's not an embedding; it's a functor, and it's an isomorphism or an equivalence of categories into C. And so now we have proven universality. Okay, but so corollary, application. And this is really what I want to go get at. So now let's take any language. So L is an arbitrary language. So I'm doing model theory now. And T is any theory in the language L. Okay, doesn't matter what language, how big the language is, how complicated theory is, complete theory, whatever you want. So we can associate a category to this, namely mod T, the models of T. So what are the objects here? I guess everybody would agree with that. These are the models of T. Well, that's why I call it, of course, this category like this. What are the morphisms? Here we could debate a little bit what we should take as morphisms. When this category is considered by model theories, one takes morphisms to be elementary embeddings, because then formulas become functors, which is very nice. It's pretty, but it's completely useless if you're doing mathematics other than model theory, right? Because there are no, well, there are elementary embeddings, but God knows they're so far and few that nobody's interested in them outside, except for us. So here I'm going to just give morphisms, what we actually call morphisms or homomorphisms. So L homomorphisms, structure preserving homomorphisms, just the usual definition. Okay, so I have my category here. Corollary, this category is universal. Proof, what's the proof? Bosch's theorem. Right? That's the proof, because what does Bosch's theorem says? That says that if you have models of a theory, then their alter product is also a model of that theory, and that's exactly what I want, right? This is to be preserved under alter products. That's the Bosch's criterion. Therefore, you get universality of this particular category. So this category is universal. And so, for instance, examples.
Hans, could I just add, what would be the terminal objects in general in that?
Sorry, you have to come a little bit closer. I didn't hear. Say it again.
The category must have the terminal object, right?
Oh, yes. Okay. Sorry. Yes. Thank you. Sorry. Okay. Missing part. So what did I miss here? Missing. So for those that are recording this and missing is here. Let's call T terminal if it has a terminal object. If it has a terminal object. Okay, so it doesn't work for any theory. It has to work for a theory that has a terminal object. Thank you. I forgot about that. Now, I don't know what that means model theoretically. There doesn't seem to be any model theoretic content to being a terminal object. But initial object is already something that model theorists have looked at more. A prime object is not the same as an initial object, but very often is. For instance, in the theory of fields, a prime field, where the from prime model comes from, by the way, is actually an initial object. Sorry, I should have said this, but if you know category T, you know that every statement has a dual statement, right? Any definition has a dual definition. So there's a terminal object, the dual of is initial object, and it just means there's a unique morphism where the arrows go in the other way. In fact, there's a very general construction. If you have a category, you take its opposite category, is the category in which the objects are the same, but the arrows go the other way, where you'll see again, an arrow does not have to be a map, a function, okay? And so, in other words, if you have an initial object, you can take the dual category and then you have a terminal object, or you can just dualize these axioms. And then you get the theory of, you get the same thing for categories with initial object, okay? So now, the examples that I have in mind, that's why I didn't notice it, because they have, of course, take the empty language and the empty theory. What you get is, of course, sets, the category of sets. And I just proved, and it has a terminal object. Okay, this is a terminal theory because the terminal object is a singleton. So I proved that mod is a universal theory. That sets is a universal. I told you I was going to prove that, right? So the same thing here. If now L is the language of groups, language of groups, and T is the theory of abelian groups, then the mod of the theory, sorry, I'm kind of making too many notations here, is of course just abelian groups, and therefore it is a universal theory. But notice how different my proofs are that this is a universal theory. This is a very general statement, almost, I mean, apart from some intricacies about isomorphism and also in class like structures. It's very what category it is called general nonsense. It's a general nonsense proof, and it works for everything. But it is very unsatisfying because this proof doesn't give me the actual actions that show that if I take something that's elementary equivalent to abelian groups, I get something that consists of groups. These axioms here that I had here, well, I only had the associativity axiom, but all the other axioms together actually gave it directly to you. So this is what I call the translation problem. So the translation problem so if you now have this, so if T is a terminal theory, so it has a terminal or initial object, whatever. So find a system sigma, so L theory, so in the language L, find sigma L-cat sentences such that mod T satisfies sigma, and if a category satisfies sigma, then C is a subcategory of mod T. It consists of models of T, let me put it that way, right? My theorem says, this theorem here, no, not that theorem. Sorry, this application here says that it's always possible. And of course, you can take all sentences that are true, all L-cat sentences are true, but that is very unsatisfactory, right? That's the same thing as axiomatizing an L structure by its complete theory. Oh, okay, that doesn't give you anything. So you want concrete axioms, like in the case of abelian groups. And honestly, there are very few cases I've tried that I can actually do this. I cannot do this for rings. I cannot do it. I don't even know how to do it for sets. It's very, very frustrating, very strange that this is such, that can this be so difficult. But on the other hand, it's not strange at all that it's difficult, because you have to, things that are, in model theory says things about elements in definable structure. You now have to define all this structure using morphisms between various objects of the same type, right? It's a totally different perspective, and this says they are the same, right? This Cavolo says they are the same perspective, but do the unraveling, do the actual translation, translate this. So this is translation problem. Yeah, it's much harder, because remember, this language, it could be very complicated. There could be a lot of symbols and so on, and all these things have to be somehow being defined. It is kind of almost magic to me, but okay. So I do two more examples, and then I want to move on. Let's see what is the time here. Okay, that's kind of what I want. Yeah.
Hear me? Before you go on, I have a problem with terminal objects. So it's just a unique terminal object, right?
It's a unique up to isomorphism because of the definition. Yes, it's a universal problem, so it has a unique up to isomorphism.
When the language has constants, I see what the terminal object is. It's just a singleton where all the constants are interpreted the same. But how has, but in sets, I mean, how do you? What is a singleton? I mean, there are many different singletons. How do you get? There's a unique map to your terminal object.
In sets, how can you, if you have a set and you want to send it to a singleton, you have to send everything to that same element. There's only one function, right? In sets, the maps are just functions. So there's a unique function that sends the elements of a set. All these elements have to be sent to the same singleton. So a singleton is a terminal object.
But,
Up to isomorphism, right? Remember, any singleton, I mean, if you take a different singleton, of course you get, yeah. But in the definition, it's the map, the morphism from the object to the terminal object that has to be unique. It's a universal problem.
But if you reverse the arrows, then the initial object should be the empty set and not a singleton. So how does that?
No. Oh yeah, you're right. No, right. It sets it also has an initial object, but that's the empty set. Yes.
You can do it only for non-empty sets, I think. You can't allow the empty set in there.
No. The empty set has a unique morph map into
empty structures.
I mean, this is a map, right? The empty map. So it is a unique map. But I agree. Look, it's very bad actually that your initial object is the same as your terminal object. And that's what happens in groups. And that's what I just wanted to explain now. But in general, you have initial objects and terminal objects might or not might exist. And often they are not the same. Okay.
Well, that's similar to in groups that,
yeah, there we have a group. So, okay, let's go to my example groups. Here, the zero group is also initial. It's an initial object. And so this is called in a category a zero object. This means there's a unique map from every group into, well, abelian or non-abelian, doesn't matter here. A unique map that sends the zero to the neutral element of the group. That's the unique map. Okay. So that's the only way you can. So here we have initial object is equal to terminal object, but in sets it's not. So often it's not, and most of the time it's not. Well, I shouldn't say that.
What is the model category without terminal objects?
No, then I don't know. I guess perhaps you could.
As soon as you have a constant, you have a terminal object.
Yeah, I think so, right?
Similar to the non-existence of the empty structure.
Yeah, okay, right. So there's a couple of things you might have to, subtleties there, but I'm not claiming to, I don't know what it does for arbitrariness. I'm just saying, let's assume that my tier has a terminal object. I don't know what the model theoretic content of that is, but just assume it. And in many cases it does. So I'm a pragmatic guy. I'm just saying, let's assume that it does, and then we are good. You'll see any element. Okay. Yeah. Okay, so in abelian groups, now another thing you can ask is, now you have this category from a model theoretic point of view, which objects are definable? Or which morphism definable? Let's concentrate on objects. Now, of course, every object is definable because it's a parameter. But so when I say definable, I mean parameter-free definable. Okay, so let me prove that the group Z plus, that's of course an abelian group or a group even, is zero definable in abelian groups. And that's the notion of a generator. So this is the definition.
Yes.
The generator J in a category C is an object that distinguishes morphisms, arrows, in the following sense. So that for any, if you have two, what is called parallel arrows. So A and B are arrows from the same domain and the same codomain, but they're distinct. Then there is a morphism, there might be many, but there is one from J to X, so that if you compose, it's still distinct. Sorry, why here? So this is the compositions is still, so the composition is still distinct. But really, I don't know how to write it. I say it, right? So that's called a generator. And Z, of course, is a generator in the group, because what does it mean that if you have a group homomorphism, which is now just a map on the elements of the group, it to be distinct. Well, I don't know why I used A and B here, but okay, I used A and B. Means that there is some point X where A of X is different from B of X. Well, how is a morphism from Z into any group is just completely determined by the image of one, right? Because it's a cyclic group. So you just have to say where one goes to, and you extend one to that element X that distinguishes between A and B. So this shows that this is generated. But Z plus direct some other group is of course also a generator, because this other group is just sitting there not doing anything, but it makes it a generator in the definition of generator. So I have to use the notion of minimal generator. It might be not the right notion. I'm saying that because MacLean in his early work has done this, looked at this also, and he has a slightly different definition of what he calls an integral generator, which of course integral means here integers. He's thinking of the integers in the same way. So, okay, but minimal generator, I mean, is a generator that embeds in any other generator. Now, you guys might say, yeah, but wait, embedding, what does that now mean? So remember that a monomorphism is a categorical notion. Injective is a notion that has to do with sets. Monomorphism is something that has to do with arrows. I don't want to give the definition of a monomorphism or an epimorphism or an isomorphism, you all know. An isomorphism is a morphism, so that there's another morphism that if you compose in either direction, you get identity. And epimorphism and monomorphism are the equivalents of surjection and injection. So when I say embed, I mean there's a monomorphism, okay? I have been used before, nobody protested, so I guess you all had this already in mind. Okay, so Z plus is the minimal, in that sense, minimal generator of abelian group. So that group is definable. That's nice, right?
Hans, one question again. This is, you probably said this already, but when you say category here, are you allowing for distinct isomorphic objects in the category? Because then, of course, Z wouldn't really be definable. It would be
yes,
a bunch of definable things.
I kind of always pretend that I'm looking at isomorphism. I look at, I somehow have take a category in which I have identified isomorphic objects. Okay. Yeah, I have been cheating a little bit here. Yeah, I agree. So okay. I don't know. Yeah, okay, but I didn't want to make category 2 is all the way. I think he's still there. So you can agree with me. This is you do this right. So this is okay. All right. So
it's called the skeletal category.
Oh, okay. Yes. Right. I knew there was a name. Of course, there's a name for all these things. But yes. Okay. So I'm kind of always looking at the skeleton, I guess. Yeah. Okay. Thank you. So I want to look at two examples. Let's call this torsion-free abelian groups. So this is a subcategory, and let me show that's universal by giving the axiom for every, so that Z is the minimal generator. So okay, sorry. Let me do it a little bit proper. So I'm saying there is a minimal generator Z, and for every object X, the map ZX is either 0 or monic. Now, what does it mean to be a zeromorphism? That goes back to this fact that we have a zero object. Namely, the initial object, the zero group, the determinant object is also the initial object. And so a zeromorphism is a morphism that factors through that zero object. Okay, so that's a very special zero map. That's very common usage in category theory. And so I'm saying in that, except for that case, of course, which is not a monomorphism, every other one is monic. Now, what does this actually mean in the category of abelian groups? This says, okay, this we know is already, it's Z plus, the cyclic group. And this says that any morphism, what is a morphism from Z plus to a group G, is just mapping 1 to something. And this just says there's no kernel. In other words, no multiple of that element is 0. So this is a torsion-free abelian group. Okay. Let's do another category. That to the opposite, I don't know. Philip, you might know this. So these are whatever, I get this thing, that the torsion category. Yeah, this torsion theory, and so this is the opposite. So the torsion groups, abelian groups. Okay, Here's my there is a minimal generator. Sorry?
Don't say opposite when you do category.
Yeah, no, that was the wrong thing. I know. I said I shouldn't have said that. That's yeah. So there's a minimal generator so that for all x, no thing is monic. Which of course says that whatever you send, every group element you send to, it has some kernel. It is annihilated by some element. Okay, and torsion Wheeling groups satisfy this. So this means that torsion Wheeling group is universal. No. Because now you have to be very careful. Torsion Wheeling groups, the theory of torsion Wheeling groups is not a first order theory. The thing is, think of this. The simplest example is take the alter product of these cyclic groups for n going to infinity, right? That's not a torsion group. It's not torsion. There are in elements of hyperfinite but infinite order. So it's not a torsion group. But so this shows that the class of torsion groups is not closed under alter products. Yeah, but wait a sec. We don't have this axiom here that shows that it does? Yeah, but look, what is this Z here? If I take an alter product of my category of abelian groups, then the generator, so I said this is the minimum generator of abelian groups. If I take an alter product of this category, that's a category of abelian groups, that's universality. But what is the generator then? It's not Z anymore because Z might not be in there. It is the alter product of Z, the hyper integers. Okay, and this is basically saying that, okay, if you have no monomorph, if this is not monic, that doesn't tell you anything. If you map from this group, which has infinite elements, to this, that doesn't mean that you're torsion free. That you're torsion. But it does mean torsion free because, of course, in the alter product, in this case, Z is a subgroup here. And so I'm just now saying if this is monic, then the restriction to Z, the actual Z, the integers, is still monic, and that proves torsion. So this is a first order category and universal. This is not. Okay, although we have axioms for it. Good, huh? Okay, all right. So I'm going to stop now, I think. Let me see here my notes, because I want to get to part 2. Yeah, I think I did kind of everything I want to say. Okay, so this is part 2. I'm now going to look at a particular category, and that's the category of compact spaces. So the category of Hausdorff compact spaces. If you're French, you can drop Hausdorff because Bourbaki says compact, and otherwise it says quasi-compact if it's not Hausdorff. So I'm going to do that way, pretend to be French. Okay, category of compact spaces. Okay. First of all, this will turn out to be not universal, but that's perhaps not immediately clear, but you kind of might guess that it's not going to be. But I will show you that a lot can be defined in it and a lot can be done with it. So it's a very interesting category from this point of view. Well, if I'm talking about topological compact spaces, it's clearly talking about topology. So where do I get the topology from? In fact, what does it even mean to have a topology if these objects are not necessarily sets? Okay, so this is the notion of a point. And here, the terminal object is going to be crucial. So it's part of I cannot do this, a lot of this theory without having a terminal object. So what is a point? So let me just, so if X is an object, then the points of X, I'm just going to write like this, is all maps of the form, all arrows of the form, where this is the initial object, right? So perhaps I should not write X's and stars. Okay, I hope this is clear. So think of sets. Remember, singleton is not the initial object in sets, but it is the terminal object in set. And so what is a map from a singleton to a set? It's just picking out an element in the set. So in case of sets, the set of points, so this I call this points, so this is called a point. The set of points, yeah, okay, so now I'm assuming that the category is small. No, it's locally small, meaning that there only set many arrows between fixed objects. There might be still, I don't care about how many objects there are, but I want the morphism between with fixed X and Y to be a set. Just to have here, this thing here has to be a set, okay, a real set. Again, perhaps it's not necessary, but okay, I didn't feel like I should venture outside sets here. Now, if we do this, if I have an arrow, if an arrow from Y to X, F, then I get an induced map from the points on Y to the points in X, just by composition, right? Remember, this is just an arrow of this kind, and where do I send it to? Well, compose it with your F, and that's the new point that you get, okay? So that's nice, and so I'll say, I call definition, I'll call my category is conservative. I'm not, I might not use the right definition. No, I'm sure that category theorists have also kind of a name for this. So I call it conservative if an arrow is monic, even only if the induced map on points is injective. And I do the same for epic and iso, and then this becomes surjective and bijective. So this concrete or conservative, I don't know. It means that a forgetful functor is conservative and faithful. That's what it kind of means. So that's why I call this conservative. All right. So this is so that I can think of, in other words, in this case, I really can think of my objects as sets, or at least they have an underlying set, and we have this. Now, let's look at the examples. In the category of sets is conservative. The category of abelian groups is absolutely not, because there are not enough points. Remember, in the category of abelian groups, so if C is the abelian groups, then a point is just, there's only one point. It's a singleton, namely the embedding from 0 into X. So it's a trivial, when you look at points, everything is trivial. It's just singletons. It's just, so there's nothing happening here. And so this definitely not conservative, this category. So categories with 0 objects, additive categories, abelian categories are not going to be this. But sets are, and topological spaces are too. In topological space, the same thing. The singleton is a terminal object. And so the more in the category of topology, of course, the objects are topological spaces. The morphisms are continuous maps. And so, right, a point, therefore, is just a continuous, what is a continuous map from a singleton to a topological space is then picking out an element in that space. So that's, it represents what happens in topological spaces, exactly what I wanted to do. Okay, that's points. But now, more importantly, where does the topology come from? Okay, so here's my definition. So X is my object in a category. So I have now a category in which I have not said really what I'm assuming about my category yet. Eventually, no. Whatever I'm going to say, whatever I'm going to do should hold in the category of compact spaces, but there might be many other categories that satisfy this, and it applies to it. Okay, so now I'm pretending to have an arbitrary category with a terminal object, an object in there, and I'm presuming already that's conservative. So I should make this in yellow, perhaps, in yellow, in red. So red are kind of my axioms. So I'm assuming that I have a conservative category. So now I have an object in this category, and so now a subset of its points is called, and I don't know I just called it cat closed. If there is an arrow such that the set theoretic image, remember for this, to this we associate a map of sets, right? So we have a forgetful functor from this category into the category of sets, and we have these arrows. Oh, I should have said it. No, I shouldn't say it. So if anything that is an image, I call cat closed. Okay, images are cat closed. Now, why can I do this in the category of compact spaces? A continuous map in a compact space is closed, meaning that the image is, in particular, it means that the image is a closed subset, and therefore a compact space again. Okay, so in this works well, and so lemma. Oh, okay. So perhaps one more definition. What is cat open then? So U in X is cat open if it's a complement. Yeah, if X minus U is cat closed. And then lemma. The cat opens on this space X for every object X, form a basis of a topology. Form a basis of a topology. So I'm going to now think of X as a topological space with respect to this new topology. Now, if you start with an arbitrary topological space, you get a very different topology than the original one, because images, of course, are most of the time not open or closed anymore. If you take the category of schemes of finite type, schemes of finite type over an algebraically closed field, then quantifier elimination of algebraically closed fields actually tells you that the topology you get is the constructible topology, if you know what that means. It's finite intersections, unions of closed and open sets. So it's almost the original topology. If you restrict yourself to the category of proper schemes of finite type over algebraically closed field, then you get actually the original Zariski topology. But in the case of corollary, if you want, comp is you recover the original topology. Because what I said, right? I just said that it was in compact spaces, every continuous map is closed, so its image is closed. So you don't get nothing new anymore. Okay, so we have now at least a topology. Oh yeah, so perhaps also corollary observation. If you have an arrow, then the induced map is now continuous. That's just the way I build things. Well, there's some theory. I don't want to spend too much on the details here because there's more interesting things that I want to say. You have to prove a couple of things here, but it all follows. It's nothing of these things is none of these things I'm saying, by the way, is very hard. Okay, up to now, there's come a part that is non-trivial, but okay. Okay, so what next? So I did points. Can't open. Yeah, okay. But this is a very difficult. In general, images are very badly behaved. So I want to have some better behavior. So if we think of closed subsets of the reals, we think of sets that are closed under limits. So limit closed. And this is called the so-called Fréchet property. So that's what I'm going to want to impose now. I want my cat closed sets to be limit closed. But a limit, what does that mean? Well, I have to have a sequence. So what is a sequence? That's a map from a countable set, an index set, to the space. So I need a countable index set. Where do I get that one from? And well, countable, I'm saying countable, but perhaps I don't even know get countable here. So this is my definition here. So this is the definition of an omega object. It's a very bad name, but so what is an omega object? It's an object that has a single non-isolated point. So like a point A in the topological space, or in this particular case, is called isolated if the singleton is open, cat open. Okay. That's meaning to say that, by the way, what this means is that this topology is discrete. Okay, no, that around the point the topology is discrete. No, not okay. I say it wrong. Okay, this is what it means. So I'm saying there's a single non-isolated point, so an omega object, and I'm going to denote it. Let's do it right here. Omega, capital omega. There's a single non-isolated point, and for any space object. I'm now thinking my objects as spaces. Okay, any space X with a single non-isolated point, there is an embedding from omega into X. I'm not saying that the embedding has to be unique, and it probably is not, but there is an embedding. Fact. So this is a fact in the blue world. Working when I say blue, I'm kind of thinking of the real world and the category that we know, the category of compact spaces. Omega is just the natural numbers, the closure of the natural number. Of course, the natural numbers are not compact space, but if I do the one-point compactification of it, I get a compact space. It's locally compact, so I get a compact space. Oh, shoot, what is this? So it's the compactification, which, of course, if you think of ordinals, it's 0 to omega. If you want, it's the ordinal omega plus 1. So the omega object is really the omega plus 1 object, but okay. Why is this? By the way, this is because this is the unique, up to isomorphism again, space, compact space. Sorry, let me write it down. It's unique up to isomorphism, countable compact space with one single non-isolated point. Yeah, what is the non-isolated point here? So the topology, of course, on the natural numbers is just a discrete topology, but when you take a one-point compactification, this is no longer, the point at infinity is no longer isolated. The opens, or at least the basis for the opens, is the terminal segments are basis for the opens here. So this is the effect of topology, but I don't know. It's folklore, so I'm just assuming it, and it proves in particular that there is that this is the omega object in my category. So I'm assuming now that I have a category. So the assumption is that I have a category in which I have an omega object where I call the non-isolated point a point at infinity, and so now I get the Fréchet axiom. It says this. We say that if the following are equivalent, if V is a subset of some space, but the space I mean now the points of the underlying points of an object in my category, is cat closed, even only if for every arrow from V to X, from omega to X. So remember, this omega object is going to be my index set, and it's going to be the sequence, giving me the sequence. So for me, a map from a morphism from omega, a continuous map, remember it's continuous, right? A continuous map from my omega object to X, such that if I take an isolated point, so I is an isolated point of omega, which is all so everything that is not infinity, right? So if A is not infinity, lies in V, then also the image of infinity lies in V. Okay, so you think of this F as a sequence, right? These are the elements of the sequence. They all belong to V, and then this is the limit of the sequence because of continuity. If you look at how this topology is defined? If you have a one single non-isolated point, it has to be an Alexandrov topology, whatever that means, and it really means this, that you're closed on the limits. So this is what I call the Fréchet axiom. And again, compact spaces satisfy this. Okay, and now you can prove, for instance, corollary. Sorry, U is cat open, even only if for every point in U there is a cat open V containing A and V is contained in U. The usual definition of openness holds. Okay, so we have now a topology, and we have a topology that is well behaved because of this Fréchet axiom. There's a lot you can do with that, but I really want to go to the catchy part here, and I don't have that much time anymore. I want to get a model of PA, piano arithmetic. I want to get my natural numbers. In the case of compact space, I'm going to get the natural numbers. Well, you might say, did you have it already? This Y. And it's the compactification of the natural numbers, and it will turn out, from now on, not everything is 100% proven, but I'm pretty sure that everything is true. Okay, so I'm going to pretend that it's all the case. So this is going to be indeed my model of PA when you remove the infinity, but I cannot prove it directly. So what I'm going to do is construct a model of PA and then show that it's isomorphic. Okay, well, I'm not going to do all that, but that's what's going on. So how do I just construct my model of PA? So a definition. So let's call it object A in my category. So now I have whenever I have something red, I mean, yeah, this whole thing should have been red, but I didn't do it. So I'm adding these axioms, right? Each time I'm adding some extra axioms, they all hold in the compact spaces, but many other things might also have satisfied these axioms. Okay, so an object A is called cat finite if its topology is discrete, if A is discrete topology as a topological space. In other words, if every singleton is open, everything is isolated points. That's a cat finite object. In cat, what happens in comp, discrete plus compact implies finite. Well, it's vice versa. So this is generalization of finite. So this is cat finite. And here you can see already that this category will not be universal, because there will be cat finite sets that are infinite, and therefore they cannot be compact, actual compact spaces. So there will be objects that are, there will be categories that are elementary equivalent to my category of compact spaces that contain objects that are cat finite but infinite, therefore they cannot be compact in the topology, in their underlying topology. Okay. So now again, I'm going to say that A is less than B means there is an embedding from A into B. That's just a notation. It doesn't mean that it's an order, it's a semi-order, right? Because A could be embedded in B and B could embed in A without them actually being isomorphic. But I will very quickly get rid of that. So why did I even mention this? I shouldn't have mentioned this here, but I made the definition. This is the definition I'm going to make now. Wait, let me see. What am I doing? Oh yeah, okay. This is my action. This is the crucial action. Definably completeness. Definably complete. Of course, when you have an order, I'm sure Alf knows, the first thing you do is look at DC. So phi is an L formula. So this is an axiom scheme. For every formula, LCAT formula in my language, okay, one variable, unary, it's a unary function. And so DCF is the axiom that there is a cat finite satisfying if there is an A cat finite set satisfying phi, then there is a minimal one. Meaning that any other cat finite set that satisfies phi has an embedding from A inside of it. right? That's what definably completeness means in this set. Remember, this is not yet an order relation. I'm not saying that it's transitive. I'm not saying it's symmetric. I'm just saying it's a relation, but it can still say what it means to be minimal for this relation. And so on. What I'm saying is that if a formula satisfies, if this formula is satisfied by some cat finite set, then there must be a minimal one satisfying it. And once you have this minimality, you can now, from this it follows, so this is a new axiom that I add to my category, and then lemma of a corollary is this is now a total order. So first of all, if A embeds in B and B, there's actually an axiom that I have to add, a pigeonhole axiom, but let me skip that kind of thing. I think it's included in here, but I haven't really thought about it. It's a total order. It's an order, right? So if A is less than B and B is less than A, then A is isomorphic to B, not equal, but isomorphic, okay? And it's even total. And again, all this you prove by using definable completeness. Of course, if you know a little bit about minimality and so on, you know that defining completeness is really the same as an axiom in inductive axiom scheme. It's equivalent to that. So okay, so we have a total order. So we have now, I'm going to define PA of my category. So wait, my category, I don't know. Sorry. Remember, C is a model of everything that is read so far in this second part of the talk, of course, and also the original axioms. So P of C is by definition the isomorphism classes of cat finite sets. So this is what I'm thinking, right? I'm thinking, okay, what are the natural numbers that are the finite cardinalities? And what's the cardinality? That's an isomorphism class of a finite set up to bijections, right? So that's what I'm trying to get now. I'm taking now cat finite sets as the cardinalities of cat finite sets. That's going to be my model of PA. Okay, I have an order relation on it. That's already a start, but I need plus and times. Okay, but I'm also assuming that this category is closed under products and co-products. Again, these are categorical definitions. They are just to do with certain maps and diagrams commute. So they can be expressed in my language, so they are definable properties, and I'm just requiring so this should be in red. So the category is closed under products and co-products. Now let's see what is this in compact spaces. What's the product in compact space is just a Cartesian product. So here is A cross B. What's the co-product is a disjoint union. That's just things that you have to accept that it's not hard to prove, but this is what it is. Now, of course, what's the cardinality of the direct product? Sorry, of the disjoint union, sorry. What's the direct? That's just adding, right? What's the cardinality of a product? That's just multiplying. And so this is what I'm going to do. I'm going to have my addition is given by the co-product of two things, the isomorphic class of the co-product of two cat finite sets. The multiplication is given by the product of two cat finite sets. And so theorem, oops, I keep pushing this theorem, P of C is a model of PA. Yay. In the category of compact spaces, of course, you just get the natural numbers, the standard model, but in non-standard compact spaces, whatever that means, you get non-standard model of PA. And remember, there are not so many axioms that I imposed so far. And so any category that satisfies these axioms, I must say, I don't know any other, I didn't really look for it, has this embedded model of PA. And so claim, as I said, it's not fully proven. PA is just isomorphic, definably isomorphic with my omega object remove infinity. So that's as I said, I think I'm pretty sure that the proof is correct. So okay, I'm going to put here a blocks with a small question mark on top of it. Now comes the real challenging thing, and I have 10 minutes for that, the reals. Because that's another very interesting space. It's not compact. Okay, it's locally compact. So the reals is locally compact. So it has a compactification. It has a 1-point compactification, which is not the one that, which is the circle. But that's not really, there's no structure anymore. The reals have addition and multiplication. I don't want to use that. The circle doesn't really have that. Well, so what I really want to do is what we do in calculus 1. I take as compactification. Compactification, I'm going to take R bar, which is R with plus or minus infinity. Okay, with the usual nonsensical operations on plus or minus infinity when you add and multiply them. Well, I guess, yeah, no, except for indeterminates. Yeah, let me not go there. We don't care about the operation. Then what matters is minus infinity, of course, the smallest, and plus infinity, the biggest. Okay, so I want to define this object. Now, even in the category of compact space, well, even in compact spaces, if I would have told you can define the natural numbers, then you might not even, you might say, how are you going to define numbers just from the fact that you know that these are compact spaces, right? I think what I'm only using is that my objects are compact spaces and my morphism are continuous maps, and somehow miraculously the natural numbers appear there. In the standard world, in non-standard world, something else appears, but it's still a model of PA. And the same thing is going to happen here. And even here, it's much less trivial than the previous case. I mean, there was kind of obvious what to do, but here it's, I mean, it's kind of ingenious idea from Freyt. So this will. Peter Freyt has done this first, and so this is ideas of Peter Freyt that we get to. But before I do this, let me say this, of course, is as a topological space is isomorphic to just a unit interval. And it's much easier to prove that. So I'm going to do first unit interval and later patch everything together to get the whole reals. So how to get the unit interval? And so this is the idea is Freyt comes up with the notion of a co-algebra. No, sorry, that's not his notion, but he has seen that co-algebras can be used for that. Co-algebra is a very general construction in, I guess, also category theory, and it has to do with an endo functor. So an endo functor is a functor on the category itself. So, but I'm not going to use so I'm still working in this. So again, I'm thinking of the category comp, but it might be something else that is elementary equivalent to it, or just something that satisfies all the axioms that I had so far. So perhaps I should put it in red. Okay, all the axioms so far, that's my C. So in that C, I'm not going to work on that category. I'm building a new category, definably from it, the category of triples. So the category of triples. What is a triple? Well, it's a triple. So it consists of an object and 2 points. So these two are points, remember points in the sense that I gave before, and they're distinct. And I think of these as top and bottom. So in the case of 0, 1, of course, it's the endpoint 0 and 1. I'm thinking this of endpoints. So a triple is a compact space with 2 endpoints. But of course, there is no order relation. So when I say endpoint is misleading, right? I don't know where they could be somewhere in the middle, whatever that means. Okay, so the category of triples. A morphism of triples is, of course, given by an arrow inside my category that sends bottom to bottom and top to top. That's obvious. So now I have a functor. The functor D is the doubling functor. So what I'm going to do, let me say first what I'm thinking of. I take the unit interval and take a copy of it, put it next to each other, and I get the interval 0, 2. And that's what I'm going to do here in general. So what I do is, if I take this guy, it's going to be a subset of the product, but a subset, the following subset. The notation is uglier than. So I'm going to take. Let me see. Let me do it right. Okay. So take x times. X times bottom. So that's a subset here, right? the other subset I want to look at is this product. So here the singleton, and here X, and now take the union of these two. That's going to be the space, and then the lower point, of course, is this point, and the top point is this point. So that's a new triple. So what does this mean here? This, if you take 0, 1, and I take another copy of 0, 1, and then rename this as 1, 2, and then I'm just saying I take the union, I take the union, the disjoint union, and I identify 1 with 1. Okay. I'm saying it this way that you see there's a categorical construction that I'm doing here. And so I get the unit interval 0, 2. It's the doubling, right? We have stretched it. Okay, preserving the endpoints. So now what is a co-algebra for this doubling? You can do this. This is an endofunctor. It's a functor on triples. It gives again a triple. So a co-algebra in general is you have a triple and you have an arrow in the category to this new triple, the doubling. Remember I said what the morphism of triples is, right? It's just an arrow from X. So this is in the case of so we have from 0, 1, we have to go to 0, 2, right? Because the doubling was 0, 2. And what is the map that I really think of is X going to 2X. That's why I call doubling. So this is an example of a co-algebra in the concrete space. Okay. And so now I can look at the category of co-algebras. So remember, co-algebra is giving an arrow like this. And if you have two arrows like that, it's not obvious what it means to have a morphism between such things. Usual commutativity, everything attributes and diagrams and so on. So let me not make that too clear. There's an alternative way of looking at this. Sorry that they have to elaborate a little bit on this. Is this equivalent with giving two maps, left and right map? So two arrows from X to X, with the condition that L of X. So right, so these are actually, I should really write them like this way. I'm going to kind of be a little bit lazy and identify a function, a morphism with the underlying map it defines. Otherwise, there's too many bars, and then so Lx is either the top or Rx is the bottom. What do I mean here? Well, let's take the graph of this function here. So this is 1 here, and here is a half. This is 0, and here put 2 and 1. A bit to scale a little bit. So the graph of this function is, of course, just a diagonal here, right? This 2x, because the scale is not the same. That's why it's slope 1. So what I'm saying is I'm bringing this down in 2 pieces. So the first piece is this one. And then, so less than a half, I want to stay within, I want to create a map from 0, 1 to itself, right? From 0, 1 to 0, 1, from 0, 1 to 0, 1. That's what is in general, in the particular case would mean. So that's the first map. This is going to be my L. You see here that L at this part L has as the top value. And then what's the other part? The other part is this guy. But I'm going to bring it down. So is this one shifted down? So this is my R. So okay, this is R, and the other guy was L, and then the sum is the total. This map is just nothing than Lx plus Rx, right? So I can break it up. So I just want to show that. But what is the advantage of this one? So if these are the when is L of X the top? This part here. This means that X is bigger than a half. So X is a right point. A point on the right. When is R of X the bottom, 0, that's here, this means that X is a left point. The reason that I give names to these points is, you'll see in a sec, because theorem 0, 1 is a terminal object, 0, 1, 0, well, sorry, no, it should, sorry. So, okay, okay, let me write down L and X here. So what is L of X? L of X is the minimum of 1 and 2x, and R of X is the max of always 0 and 2x minus 1. So these are the concrete formulas for it, right? Okay, so the theorem is now that if you take 0, 1, with this co-algebra that I just described to you, is a terminal object in the category of co-algebras. We know what the terminal object is, so it means that every other co-algebra has to map onto this guy, not onto, has to map to this guy in a unique way. Okay, proof. And this is the observation that Freud made, that this can be done. And the proof is actually very simple. Once you understand it, it's binary search. So what are we trying to do here? Okay, so we have X here, and here are my two distinguished points. I'm not putting them at the end because I don't know what that means. But here, of course, I have 0, 1. So, sorry, let's make a picture. Oh. So here I have 0, 1. Oh, I'm getting over time, so I'm going to do this quickly. 0, 1. So what do I do? Suppose I have a point here, and it has to be mapped somewhere. And why should it be mapped here, for instance? Well, let's think. If it maps here, it means that each image is bigger than 1. How do I detect bigger than a half? Right? This is a halfway. How do I detect that? How do I take that this was because this is the right point, right? So if X is a right point, remember, this is what this means. You can detect it from the algebra. So this generally given, so we have this X, this co-algebra with these two maps, right? And from that, I have to define now a map to 0, 1. That's what I need to do. And so I'm saying, what do I do? Well, you look for this point and say, is it the right or the left point? Binary search. If it's the right point, then it has to be mapped somewhere on the right side of this interval. Okay, so what I do is, if it's the right point, I said, the first binary digit I put equal to 1. I'm going to do binary digits. If it's a left point, beta 1 should be 0. Okay. And now, what do I do? What do I look like? So Z of X is now R of X. So define it to R of X. So I'm doing it on this particular example, right? So remember, either L of X is trivial or R of X is trivial. I now take the non-trivial value, which brings me back into 0, 1. So in this case, I would have identified this part now with the original part. So this time it's less than 3/4. So this will be a left point. This will be a left point now. Oh, sorry, this is bad. This is now going to be left. It falls to the left. I check this by my L, applying L to this, and so if L of Rx is detected by R. Sorry, it's R that detects this. R of Rx. Sorry, R of Rx is bottom, so this means it's a left point. So this means that the second binary digit should be 0. And I keep doing this. So each time I map, I do the doubling, and then I shrink back. And I see again whether I'm left or right, left, right, left, right. If it's right, I put a 1. If it's left, I put a 0, and I get binary digits. And at the end, I get a binary number, beta 1, beta 2, etc. And that's going to be the image of my little x. My point x is going to be mapped to that real number. So that's the binary search algorithm. This gives you, that is a terminal object. And so now I'm over time, so let me quickly say what the conclusion would be. You now impose this as an action, that there is a terminal co-algebra object that you call then it's unique because it's terminally has make it unique. You call that the unit interval, and now you show the unit interval has an order relation on it. It has a midpoint which gives you addition, and then once you have unit interval and you also have the PAA, the model of PAA, you take the product and identify. So now you take you think as intervals put next to each other, put them all next to each other, and identify the endpoint of the previous one with the beginning point of the former one, you get a definable reals that are your non-standard reals. And then I claim that this is if you can do multiplication, I claim this is a real closed field. And that follows on in the fact that any continuous map that preserves triples, any map of triples has to be an epimorphism. If you have to, this is the intermediate value theorem. If you send 0 to 0 and 1 to 1, a continuous map that does that must cover everything. And that's the intermediate value theorem. And if you know that a field that satisfies this is a non-minimal field. So my claim is that you get a non-minimal field, but sorry, I'm running out of time, so I cannot describe it fully to you. Thank you very much.